Alright, next we have the constant multiple rule. So the constant multiple rule states the following. Again, I'm expressing this as theorems. I'm not proving most of them. I'll prove some select ones that don't take too much time. You can always find the proofs of these things online. The constant multiple rule says the following. If f is a differentiable function, and c is a constant, in fact a real number, then c times f is also differentiable, and the derivative with respect to x of c of f of x is equal to c times f prime of x. So basically what this is saying is that if you have a constant multiplied by times a function, then it is the same thing as taking that constant and multiplying it by the derivative of the function. I'm not going to prove this. Maybe during office hours I'll prove it if you want to see it. It's a short proof, doesn't take too long, but I want to focus on the examples. So for example, let's say you have y equals 2 over x. Then y prime is equal to, first of all, let's separate this a little bit. This is 2 times 1 over x. I mean, this is y, so this is still y. This is 2 times 1 over x. So I could just take the derivative of this first and then multiply by this constant. And that's what I'm going to do. So first of all, let's rewrite this one more time because I have the x in the denominator. So this is 2 times x to the minus 1. And the reason why I'm doing this is because now this will allow me to use the power rule. If I do this, I could now use the power rule. So, and this will be the one case where I'll actually it will be beneficial to use this notation. So d dx is the same thing as it's equal to d dx of 2 times x to the minus 1. That's the same thing as, we could take out now the 2 from here because the 2 is just a constant. This is just d dx of x to the minus 1, and this just means that we're going to take the derivative of just this, not the 2. Well, I'm going to do that on the side. If you remember, and here is going to be equal to minus 1, and then minus 1 is going to be equal to minus 1 minus 1, which last time I checked, that's negative 2. So this means that what we have here is the derivative is going to be equal to 2 times n x to the n minus 1, right? But we know what x times n to the n minus 1 is. That's just simply equal to negative 1 for n, and then n minus 1 is equal to minus 2. And then when we multiply in the 2, when we distribute the 2, we have negative 2 x to the minus 2, and that's just simply equal to negative 2 over the square root of x. No, 2 over x, negative 2 over x squared. It's not a half. So negative 2 over x squared. Sorry about that. And that is the derivative of y equals 2 over x. So again, you could, what this is saying, what the constant multiple rule says is that if you're multiplying a constant times a function, then you simply take the derivative of the function and then multiply by the constant. This is not the same, so note, not the same as doing, let's say, the derivative of 2 plus x. That's completely different. Um, not the same. So just keep that in mind. Let's do another example. So I have, let's say, f of t is a function of time, is equal to 4t squared over 5. The derivative here, let's rewrite this first. This is the same as 4 over 5 times t squared. You could do this. You could take the fraction and separate it. The same concept, n is equal to 2, n minus 1 is equal to 2 minus 1, which is 1. So now we know that f prime of t is going to be equal to 4 over 5, this is now where we actually get to speed up the process, times 2t. I'm going to start speeding up the process a little bit now, because I think now you get the point. You bring down the 2, and then you minus 1 from it. That's all we're doing. Now notice that I'm now multiplying the 2 times the 4 over 5. So that means that f prime of t is equal to 2 times 4, which is 8, over 5 times t, or simply 8t over 5. So that is the solution for this problem. Okay, let's do another one. What about if we have y equals 2 times square root of x? Well, like I said, rewrite it. This is 2 times x to the 1/2. And now, you know, the derivative of x to the 1/2 you could do on the side. Notice n is equal to 1/2, and n minus 1 is equal to 1/2 minus 1, which equals negative 1/2. So we have now that the derivative of y prime of this is going to be equal to 2 times the derivative of x to the 1/2. But the derivative of x to the 1/2 is going to be equal to 1/2. Bring down the 1/2 to the front, and then you minus 1. So it's going to be 1/2 x to the minus 1/2. And that's why I wrote it on the side, because it's clearer for you to see it. We could simplify this a little bit more. 2 times 1/2 is just 1, so they cancel, and you're just left with x to the minus 1/2. But x to the minus 1/2 is the same thing as 1 over square root of x. So the derivative of 2 times square root of x is simply 1 over square root of x. So another example, number 4. Y equals 1 over 2 cubic root of x squared. Again, rewrite it. First step is going to be to rewrite it. So this is 2 times x to the power 2 over 3. And now rewrite it once more. You know, take the 1/2 out. So this is 1/2 times 1 over x to the 2 over 3. And then bring the x to the numerator. So this is x equals 1/2 times x to the minus 2 over 3. This just makes your life easier to see what's going on. So this is n is going to be equal to minus 2 over 3. N minus 1 is going to be equal to minus 2 over 3 minus 1, which in this case is going to be minus 2 over 3 minus 3 over 3. And here, because of in the numerator both of them are negative, we're just adding. So it's going to be minus 5 over 3. And now we could take the derivative. So y prime is really equal to 1/2 times minus 2 over 3 times x to the power minus 5 over 3. And then you could combine this. You could do the multiplication. Again, when you multiply fractions, you multiply across. So this is going to be minus 2. Actually, you could even cancel. This is going to be minus 1 over 3 times 1 over x to the 5 over 3. Which just means that you have the derivative is going to be equal to minus 1 over 3x to the 5 over 3. Okay. So most of this boils down to algebra. The derivative step ended when we went from here to here. That's when we took the derivative. Okay. So everything after that was just algebra. let's do one more. And notice that for most of this I was going a bit faster. Only the first one that I took a step by step, which ideally you will take the derivative in terms of x of each term. I'll do the last one like that just so we could review that as well. So y equals minus 3x over 2. So that means that y prime is going to be equal to d dx of minus 3x over 2, which is the same thing as, again, you could pull out the minus 3 over 2. You will take that out of the derivative, and then you will take the derivative with respect to x of just the variable x. And this is something that we actually haven't really seen. So n here is 1, and n minus 1 is going to be 1 minus 1, which is 0. And if you remember, any number to the power 0 is just 1. So what we have here on the inside, so d dx of x is simply 1, because that's just going to be 1 times x to the 0, but x to the 0 is 1, so that's just 1 times 1, which is 1. So really what we have here is minus 3 over 2 times 1, which is just minus 3 over 2. So this derivative, the derivative of negative 3 over 2x, is just minus 3 over 2. So simply the x goes away. You could think about it as the x is turning into a 1, or if you were like plugging in 1 in there. But only when you have x to no power, to the power 1. So here we combine, so notice here we combine the power rule and the constant multiple rule. And what we had was the following. We have that the derivative with respect to x of a function x to the n times a constant c is the same thing as c times n times x to the n minus 1. So simply it's just c times the power rule. Remember the power rule, f prime of x, if f of x equals x to the n, then f prime of x is n times x to the n minus 1. So this is simply, what we have here is simply c times f of x when f is x to the n minus 1. X to the n, not x to the n minus 1, x to the n. Okay? Let me do one more example just for practice. I'll do one more. What number was I up to? 4. So let's do one final one, 5. So what if we're dealing with the following? Y equals 7 over 3x to the minus 2. Well, if you're dealing with something like this, again, the first step should always be to rewrite it into something that looks simpler. So this is just 7 times 1 over 3x to the minus 2. And then if I were you, I will bring that to the numerator. Well, actually, so we have this to the minus 2, so this is actually 1 over 3x to the 2, because the minus 2 here is in the denominator. But here, what we have, I'm going to do it on the side, just so that you can see what's going on. Scrap work. What we have here is it's a complex fraction. So what we have here is 1 divided by 1 over 3x squared. And this is really just 1 over 1, the numerator. So you could use the keep change flip method, and this is really 3x squared over 1, and you could multiply across. So what we really have is 3x squared here. So this right here simply turns into 3x, the whole thing squared. And this is just a rule from before. If you had 1 over a to the minus 1, then this is just a to the 1. Okay? So this is the reasoning why. Now that we have rewritten it, well, what can we do? We could actually could actually now take the derivative if we wanted to. So we could take the derivative. So this is, no, not to take the derivative. I'll first expand this. So this is going to be 3 squared is 9. So we have 9x squared, and then 7 times 9, I believe that's 63. So this is 63x squared, and now we could take the derivative with respect to x. So I'll do it. D dx of y is going to be equal to derivative with respect to x of 63x squared. Well, this is the same thing as 63 times the derivative of x squared. But remember, x squared, n here is 2, which means n minus 1 here is 2 minus 1, which is 1, which just means that this is the same thing as 2x. So this is 63 times 2x, which is 126 x's. So we have that the derivative of y is 126x. So that is how you use the constant multiple rule. Thank you for your time.